are, is a lot of you have never seen what's inside these things, and then what we're doing to make this long battery life product for people who want it, and then where the trends are going in the industry, and the types of things we do with the battery pack level from both a safety and a performance and reliability perspective to address what customers want and what we think will be useful for customers. So the very beginning are cells, which are what's inside battery packs. And there's three basic form factors, and they're all similar chemistries. So when you hear all these different terms about cylindrical cells or prismatic cells or polymer cells, they're all similar chemistries. That's a cylinder. This is the workhorse of the industry, cheapest dollar per watt hour you can get on the planet. We like numbers because we're engineers. That's called an 18650. It's 18 millimeters by 65 millimeters. And because of the standardization of all the equipment and the form factor, you can put them in multiple products and change them out very easily with different suppliers. So the innovation for years has not been innovation, it's just been packaged more into the same size can. 10 years ago, it was 1,600 milliamp hours. Right now, we're about twice that, about 3,200. And they're cheaper because of the millions that are made. Started in Japan, moved to Korea, moved into China. There's one innovative group from Vancouver that made a splash several years ago, the NEC Mali, who's now bought by a Taiwanese company and are not doing so well. But other than that, it's all manufactured in Asia. This is a prismatic cell. It's still a can. The manufacturing process, I didn't bring any of the bits and pieces. Usually I have what we call, the technical term, a jelly roll that goes inside a can. So you've got an anode, separator, cathode, separator material, wind it all up, put it in a can. You wind it up, that's a jelly roll. If you wind it on a mandrel that's diamond shape and then squash it a little, you get something that's prismatic. And it's still in a can, so it's still very robust. This was originally developed for the early cell phones. And this is a standard, one of the few standard prismatic sizes. One of the challenges we have is standardization when we go to this thinner and thinner form factors now. And these are, the industry calls them pouch cells. Everybody just calls them polymer cells because the original ones had polymerized electrolyte. So after you shove your jelly roll in, you put in some electrolyte to allow the ions to move. Most of these are made the same way, believe it or not. It's anode, cathode, separated material. But instead of being wound, it's folded. And you can imagine that's a much slower process than putting them on a machine and spinning them up and putting them in. And then they're putting this aluminum pouch with a coating for insulation. So it's not real robust from a mechanical standpoint. If you can scratch it with your fingernail and cause it to leak, and there's some problems with handling them, but to go thinner, this is the way we have to go. It's not all cookie cutter either. Everybody seems to think, we can make them any size we want. And yes, that's true. There's machinery concerns, and there's a certain XY sweet spots from an energy density standpoint. The thickness, you get better energy density as you're thicker, as you can imagine. Once you start getting to like 3 millimeters or less, your outer covering is more and more inactive material taking space in there. So, you can pick these up, handle them. They shouldn't hurt you, I don't think. I think they're pretty much old and dead. But that's the cells. So we stack these up in battery packs in different forms. It's usually, in notebooks, it's been 3 series, maybe 2 parallel, or 4 series, 2 parallel, sometimes 3 parallel.
And that's what they mean by cells. Each one, when we
These
say
are cells.
when we say a 6-cell battery, there's 6 of those. 6 cell versus a 9-cell battery.
Precisely. So going to our 24 or 32 hour time targets, it's really just a matter of doing how much energy your notebook's using and how many watt hours you can put in a battery pack. There's regulatory limits. Regulatory limit is 100 watt hours in your battery pack or less. Otherwise, you have to ship it as Class 9 hazardous materials. So very few people do that. They have to do that for like the EV batteries and stuff like that. So by what you guys have been carrying around, you've got a standard 9-cell battery. It has 3.0 amp hour cells. You do the math, it comes out to like 99.9 watt hours. And then you stack another one with the same in it, and you've got 200 watt hours of energy. It's the most you can have in 2 batteries and carry it around without these regulatory issues. So, basically you're talking about an average power use of about 6 watts when you divide it in there, and you get about 30 some hours. If you use 7 watts of power with your notebook, it comes down incrementally. So it's all about how much power in the power management that really has allowed us to make big steps in battery life. It's not the battery technology itself. The battery technology itself has been incremental growth, like 5% year over year from an energy density standpoint.
And with your notebooks, you can actually see how many watts you're using. We've got software in there,
right.
The HP Power Manager software that allows you to set it. But if you're truly interested in the math behind it, you can see that, look, doing this, running the DVD or whatever, I'm burning 8 or 9 watts an hour. It's kind of in standby, it's 4 or 5. So you do that by John's math, divide it out by 200, and you're going to get a rough estimate on where you're going.
Exactly. And because that's dynamic, even the power manager isn't accurate. That's what's inside what you got. A lot of air. That's for ID. The previous generation, we had 12 2.2 amp hour cells because that hit that 100 watt hour. But with the newer 3.0 amp hour cells, we can put more cells in use fewer cells and get the same amount of energy. So it's actually lighter with the same amount of power as our previous generation, which is nice for a change. It's a pretty big circuit board, and that's because we can charge it externally with the AC adapter. So that requires having a charging circuit in the battery pack itself. The other nice thing about this configuration, it's really easy to make. It's 3 series, 3 parallel. And what you get from that is not only the extra power, but you get really good lifetime out of this thing. Very good charge-discharge cycle life because you never stress it. When you put 3 cells in parallel, your power is getting split through 3 stacks. And it's real easy on the cells. The faster you discharge a cell, the quicker it degrades over time. And that's the key thing that customers need to understand about batteries is they're consumable. With going to thinner and thinner form factors and these polymer cells and ones that are embedded in the notebook, the big concern is now, can we have a battery that's not going to die after 1 year or after 2 years? Because typically we've got 1-year warranties on battery packs. So I'll get into that in a minute. The other accessory pack is the extended pack that you dock with. So it's got a big chunk taken out of it. Obviously you can't dock with that because this is where the dock is. And again, the new generation, should have snapped this together all the way, has polymer cells in it to maximize the space better. You can, engineering sample, there we go. So this one does not have a external charger. It just plugs in the bottom of the notebook and you can put it in the dock with it on it. This is about 73 watt hours. But to maximize the space better, we've taken these polymer cells, we've stacked them 2 high in the back, 5 across the front. The assembly process is much more difficult that way because you don't have just a nice weld everything together. But it's not bad. You get 3 in parallel and 3 in series. It's a 9-cell battery, just like this one. It's just less watt hours, and it keeps that low profile. The challenge is making these things to fit a variety of notebook sizes, right? The P series, you've got 13, 14, even the workstations up to 17-inch. And there's a there's a margin on that dock angle that you have to hit with these products. So from an ID and a mechanical perspective, there's a lot of challenges to making it work across the different products. So that's the latest stuff. The previous generation had used prismatic cells and was only about 58 watt hours, something like that. So those are the two extended packs that get us to those 24, 32 hour targets. Now as we get thinner, it gets trickier. Before I get to that, I'm going to just show you typical battery packs, like your standard stuff, so you can see what we're doing. This is for one of the small, like 11, 12-inch products. Here, this one's smarter, so I didn't get the top stuck on it. But this uses prismatic cells to get smaller than that 18 millimeter form factor, because if you're using 18650s, you're stuck at 18 with plastic. So, you know, your Ultrabook 21 millimeter, 22 millimeter, it's really tough to do with those unless the battery comes up in the back and the hinge up goes over it, you know. But this is a little 4-cell prismatic battery, and you can see how clean and pretty this is. All your electronics are on a board here that do all your battery management. This is basically just for the connector. So the engineering has gotten pretty small and tight. It gets more expensive, and that's the trade-off. All of these form factor improvements are about trade-offs. And when you compare that to a standard cylindrical one that we're doing right now, you can see this one's a lot fatter. And it's got twice the energy. So you need the standard cylindrical ones for, you know, improved runtime and things like that, where thinness isn't a factor. And it's cheaper. The cost is much less. When you start looking at dollars per watt hour, this is probably twice what a cylindrical cell is. These guys are probably 1.6 or 7. So thin costs money is really the message here. So we have to be choosy about which products we go to these thinner capacities. So now, as we get to the Ultrabook world, and our friends at Intel reducing power even further, this allows us to put embedded batteries in with a little more confidence that they're going to last, 3 years or more, life of the product. And we have to treat them well to do that. The secret, if there is one, is don't charge them fast. It's probably the biggest complaint people make about their iPads. If you don't charge it fast, it'll be better. It won't die as quick. What'll happen is, because these are not in a can, they can swell. That's a double-edged sword. The good thing about that is, when you allow a battery to swell, the electrodes don't break down and they last forever. You don't have to do anything to these guys, and you can get 1,000 cycles pretty easily if you allow them to swell. Now, if they swell too much, you get cracked plastics. Everybody's seen this. It's been going on for a long time. So to mitigate that swelling risk, the easy thing to do is charge it slow. The difficult thing to do is find a way to charge it where you can still get it in, maybe 2.5 hours, but not charge at a high rate at a high voltage. So we're doing a lot of different types of charging functions. We've done a lot of experiments. One of our first notebooks in a long time, a little Harbor Mini, had a polymer pack, and we had started to ship it and got some experimental data back in and said, hey, we really need to alter our charging regime in the notebook, and we put out a service BIOS flash to handle that. It's the first time we'd ever done that with a battery pack, which was kind of fun and scary at the same time, but it worked. And going forward, there's a lot more innovation on the charging as opposed to the cells themselves. The cells, it's chemistry. when you look at energy density, these guys still have a higher energy density at the cell level, because you can compress things more. It'll stay in that shape. You put it in the can. About 700 watt hours per liter is the top. You'll see in this form about 500 watt hours per liter in this form. But when you start talking about at the pack level, it uses your space better. You can be innovative. You can move it around.
And most of the Ultrabooks are going to the
Non-replaceable,
No, yeah.
right. So here's an example of, this is Spectre's battery, which is pretty cool. It's 4 polymer cells with some electronics, little pigtail there. It gets screwed into the bottom of the notebook. It makes it very easy service replaceable. It makes it very easy user replaceable if somebody goes on YouTube and sees how to take their notebook apart. But you can see it's not just bare cells sitting in the notebook. It's still encased in a bit of a frame, with some mylar to protect the cells, and the handling that happens at the ODMs. The guys like Quantum and Compal, Wistron that are making the notebooks for the industry don't make battery packs. The guys who are making the battery packs have had to go through a lot of training to handle these cells properly. We can thank our friends at Cupertino for being, they went 100% polymer cells probably in 2005 and had a lot of difficulties with it, but the packers learned from that, and we learned from that, and we think we're doing it better because we've learned from the industry's lessons. And you can see it's not about weight either. This is, if you feel that, it's not light. The batteries, it's the same kind of chemistry. So if you want the same kind of watt hours, the batteries aren't lighter. There is one type of chemistry coming up that actually been around for a dozen years, which is lithium sulfur, but it's a metal, and it's very light. Good. We call it gravimetric energy density. Very light, they're like pillows, but volumetrically they're big, which doesn't fit well in consumer electronics. And when you have metal issues, they burn like nobody's business. You can't put them out with just water or standard techniques.
Back to the weight issue again. When you get to the Ultrabook market, there's trade-offs to be made. Now, I'll use kind of the Folio 13 or Spectre, for example. So Folio 13, I think many of you have had a chance to see it. It's 3.1, 3.2 pounds. Yes, there are some 2.7 pound Ultrabooks on the market, but the difference in battery, we're going 9 hours, they're going 4. So again, that trade-off, to John's point, these things aren't light, but the more cell density you pack in there, the heavier they get, correct? So
that's correct.
It's a matter of taking that right balance of finding, how much battery can I deliver in the right amount of weight,
And you can go 2 different ways with it. Everybody has the same suppliers for the most part. A big part of my job is new supplier development, so I'm finding guys who can maybe do it a little cheaper. The chemistries are the same, but we're looking at an industry where everybody's got the same stuff. And when you start talking about cost, everybody says, oh, well, if you standardize on the same cell size, we can drive the cost down. Well, selling notebooks is all about ID these days. And with the battery playing such an integral role in the product ID, everybody's going to have their own custom cells, as it were. And that's keeping the cost up in the industry as well. But it allows us to be a little innovative. We've done some things like the Folio product was much different than this. It had 6 cells, which were slightly smaller, stacked them 2 high on either side of the touchpad, 1 under the touchpad and 1 under the keyboard. So it was like this kind of shape. But because it's getting screwed in the notebook and not handled by a user, you can do that kind of thing. So
that's where our innovation comes in, right? I mean, like you said, the parts are, we're all taking, I don't say parts off the shelf, we're all taking those parts. And then HP and John and his team take that innovation and do some things on how you place them that, and as well as safety, because I think it's not fair to say we're all taking the same parts, because we do a lot of things that other people don't do when it comes to some of the safety stuff as well.
Yeah, that's right. So, 2 things I do in my lab. I do cell testing. I actually do safety testing, overcharge testing particularly, because lithium ion, that's the dangerous place where lithium ion goes, is if you overcharge it, it overheats. Now these polymer cells are not so bad because you just can't build up a lot of pressure inside of them. They split and they vent, but they still, have awkward moments. These guys can exhibit something we call rapid disassembly, where blow their tops off, eject contents, things like that if you overcharge them. And not just overcharge them, but if you expose them to high temperature, you can exacerbate some conditions with them. So lithium ion is not a friendly chemistry. It's gotten better over time, and manufacturing is the key. So getting into factories and looking at quality control systems is critical. In December of 2010, we took a 5-person task team and did a deep dive quality survey of the battery packers, just the same way we go to the ODMs who are making the notebooks. And you do a deep dive, quality improvements, and we're doing a follow-up in June of this year, so about an 18-month follow-up. But we've got guys who are in there almost every week looking at what the issues are. The big issue used to be contamination. It still is, as far as the process of making these things. There's metal everywhere. And you get little bits of metal where it doesn't belong, and that's where the industry has had issues in the past. The testing I do is basically looking at design. As you put more and more energy into the same space, you need to be able to dissipate that energy safely if something happens. So the vent structure has been redesigned over the years and things like that, but not without blowing the doors off my test chamber a couple of times. Second thing we do is we've driven a lot of quality improvements into the battery packs. Since about 2004, 3 key elements have been driven in everything we do. One is there's no loose wires in any of these. You don't see wires anywhere. If you look at anybody else's batteries, you'll see wires running from circuit boards or between cells even. It's pretty crazy, because in the past that's been the reason for some recalls, where wires got pinched and charging voltage was delivered across one cell instead of 4 of them or something like that. So it serves 2 things. A, it's safer. B, it's easier to make. It's easy to look at the cost of the materials. It's cheaper to just buy wire and have somebody solder it on. But the manufacturing process is quicker, easier, more reliable when you have a harness like this. You just put it on, solder, you're done, instead of taking a bunch of wires. The other thing we do is have a conformal coating on the circuit board, and that conformal coating, you can't see it because it's clear, but it protects the circuit board when it's being attached from little solder balls or anything that might pop off in there to cause issues. It also protects it if late in life one of these cells decides to leak, and it does happen. People might leave these sitting on a shelf for 5 years, and they'll leak just like any kind of battery over time. There's corrosion and stuff. And it protects the circuit board from the electrolyte and something from flaming that way. So we have the flat interconnects, we have conformal coating, and what else do we have? Probably the same thing as the rest of the industry now. Those are the two key things I haven't seen in everything.
Another reason, again, I'm not going to give you a sales pitch to buy HP parts, but as the #1 notebook vendor in the world, there's other third-party batteries out there. They're not made to the same standards that we manufacture to. Will they work? Yes. Are they the same quality, same safety standards? Absolutely not.
Yeah, and we've had customers come in, big customers say, who may be in the same general corporate structure, say Duracell. Can we use a Duracell battery? Well, who makes Duracell's batteries? It turns out it's some guy who has a website in the West Coast somewhere, or Best Buy was sourcing stuff for their warranty purposes, and we've gone real heavy into pushing, our batteries as the second sources. And Customs has gotten real sensitized to this as well over the years, and one of the things that I do as well is look at customs captures at counterfeit batteries. There's a lot of ones that will say HP on them. Somebody bought them on eBay, and 90% of them are coming out of Hong Kong via Shenzhen in South China. So there's a lot to be wary of with third-party batteries.
So most of those batteries, those third-party batteries, wouldn't have like any of that conformal stuff to protect it from battery leaking or any of that stuff.
Yeah, typically they don't. They'll have a bunch of wires and usually cells that I've never seen before. Because
Like
right now,
what type of cells?
well, cylindrical usually.
Okay.
I haven't, the polymer stuff's so new now. We haven't seen a lot of that yet. But the cylindrical cells, we are basically using a handful of suppliers. It was Sony, Panasonic, and Sanyo in Japan. Now, Sony's out of the energy business. They're just doing power cells. Sanyo and Panasonic are now Panasonic. So basically we've got Panasonic. And I really sympathize with the Sanyo guys because they went through the same thing Compaq did. They were the little guys being bought by the big guys, but they took over the battery part because they were the bigger battery company. And then there's the Koreans. There's Samsung and LG, who are combined much bigger than the stuff coming out of Japan. And other than the two Koreans and Panasonic, there's a couple of Chinese players that we've spent years trying to bring up, but have not been economically able to sustain stuff. There's one guy down in Shenzhen, BAK, that's traded on NASDAQ. And it was actually the Mali guys from Vancouver that were running that factory for a while. But because they weren't a Chinese government-owned company, they didn't get the same kind of perks, and weren't able to compete as well. They're still there. They're still making product, but and they're still qualified on a couple of our battery packs. We just ship very little of it. And then there's a couple of up-and-comers. There's a guy's Amprix Technology, ATL, that was the first big polymer cell manufacturer that decided to go cylindrical back when there were a couple of shortages in 2008. They're now out of the energy business too. They're doing it's all about EV. And there's another guy, Lishan, up in Tianjin. But really, there's three big guys, So, and you can tell whose cell they are usually just by looking at them. They're all different colors. That's an LG pink 3.0 cell. There's all of the Sanyo / Panasonic have a red coating on them. Sony's are green.
I have an adjacent question about recharging. That's okay. Is it a myth that if you run a battery down low early in its lifetime and then recharge it, and then do that a few times at the beginning, that the battery will actually last longer?
No, that's a myth. It's lithium ion. It's not like nickel metal hydride or the nickel chemistry. Nickel chemistries, that was true.
Okay.
You wanted to learn that whole capacity.
Right. Yeah.
Lithium is like a bucket. You're pouring energy in, pouring energy out. The issues with lithium ion is you don't want to let them sit on the shelf too long. And this is what I was talking about at the conference a couple of days ago. Is these guys, if you get to a low voltage condition like 1.5 volts or less, nominal voltage is 3.6. We usually cut off discharge at about 3 to 3.3. Depending on the product, you charge up to 4.2. So 1.5 is very low, but it can happen if you put it if you leave it in a unit that's sitting on a shelf for probably 9 months to a year, it'll swell up, and that's because the low voltage initiates some chemical processes and outgas.
Well, you actually just hit on a question that I was going to ask, because the swelling issue is definitely a major concern with lithium polymer tech. All three of the lithium polymer based products that I have that are older than 4 years old have had catastrophic swelling failure.
Crack the plastics.
Yeah. So when you are moving to lithium polymer cells in devices and you essentially make them integrated so that they are not easily removable, and then you just talk about the fact that you don't want to leave them in the device for a long time, what's HP doing besides adjusting the charging cycles and how quickly you charge it?
Well, we've raised there's two things you can do on the low end. One is the easy thing is you just don't use the lower part of that chemistry. You cut off at 3.3 volts, then you have more time before you get to the safety cutoff limit. The safety cutoff limit has been like 2.5, 2.6, where it shuts down all the electronics and goes basically into sleep. And from there, to get to that 1.5 or so might be, a year. If we can raise that safety cutoff, you can buy yourself another year or so. It's still going to happen if people let them sit there for 4 years and don't do anything. I'm working with the cell manufacturers on additives to minimize the outgassing in low voltage. But, you're still going to have opportunities. If it's, 1 in a million, we're going to see a bunch of them,
How many people after? If you're not using, most people are using their notebook on a regular basis. Again, just another reason to dispose of these things properly. When you get rid of consumer electronics, you should recycle them properly rather than just let them sit on your shelf.
It's a customer education more than anything, and we work with with our service team on customer advisories. We had to do that with the Mini when we had some swelling issues because of the charging. But in general, we need you guys to help us educate customers. That's where the value of the press comes into play. You buy something, you don't listen to what the manufacturer's telling you. You're out there seeing what everybody else is saying about it, right? So that's where it's customer education. And any other thing that happens is other than the long sitting on the shelf thing, to get the long life of the battery, is you just don't quite charge it up all the way. And that's one of the strange, innovative things that we did with cylindrical cells originally. Back in 2008, we started selling the long life batteries with a 3-year warranty to our commercial customers who were purchasing 3-year warranties for the notebook. And the innovation is less innovation, and we're just being clever, because the industry's known for years that if you charge up to maybe 4.15 volts instead of 4.2, all of a sudden your cycle life, instead of going like this, all of a sudden it flattens out and you've got 1,000 cycles with cylindrical cells by not using all of it. Tesla motor cars took this one step further. They're using standard 18650 cells in a Tesla motor car, over 6,000 of them.
Those
6,000 those pink ones?
Not the pink ones. They're using a 2.4 amp hour cell that Panasonic and Sanyo make. It's about 6,500 of them, and they're strapped in water jackets for cooling, all these sensors to monitor them. But what they do is, instead of operating from 4.2 to 3.0, they're operating from about 3.9 to 3.3. They're using about 50% of the energy that the cell is capable of. So they're not going all the way up and they're not going all the way down. It's very strange. Very strange.
And that allows them to get a much longer life cycle on
Yeah,
that?
much longer life cycle. And the funny thing is, there's chemistries that'll give you a longer life cycle or give you faster charge capabilities. One of the things they wanted to do was charge fast. That's what EVs are all about. Notebooks, you can go down a fast charge path where you can get 80% in 30 minutes, but the trade-off is your energy density is less. They don't pack the materials as tight in a cell. There's actually one polymer cell out there that one of our competitors is using in a product that advertises that. And the fact is, you need to. It's only like a 30-some watt-hour pack, and you need to charge it every day at lunch because you can only get about 2.5 hours out of it. So it's a small. It's the same size as the kind of stuff we use, but the energy density is less, so they get less runtime. But you can charge it fast. Is this something we can sell? Maybe, but.
It's an interesting trade-off. So you got,
And we've
you
talked
can
about it
charge
all the
it,
time.
get it charged all the time.